For decades, prosody research maintained a strict obsession with the acoustic realm. Linguists quantified human speech by isolating audio variables, measuring pitch contours, tracking duration, and graphing formants. That auditory-first approach created a severe bottleneck in conversational AI. It produced artificial systems capable of generating perfectly intelligible human sounds, yet they still communicate with the rigid, unnatural cadence of a robot. Expressive human communication relies on a continuous stream of auditory data heavily qualified by visual signals. We rely on extralinguistic prosody, the eyebrow raises, the head nods, and slight smiles. These physical gestures actively alter the semantic meaning of the words being spoken. To engineer conversational agents that actually communicate, we have to map the exact subconscious hierarchy the human brain uses to fuse acoustic signals with visual gestures. Early synthetic talking heads relied on parameterized 3D wireframes, using text-to-speech rules to deform the mesh. Synchronizing lip movements to phonemes ensures intelligibility, but not communication. Acoustics alone produce a dead upper face. Without expressive parameters like raised brows, the output fails to convey emotion. Natural visual speech relies heavily on co-articulation. The face requires constant anticipation of upcoming mouth shapes, preparing the facial muscles for the next sound rather than strictly reacting to the current audio. Escaping the uncanny valley requires mapping the cognitive rules of real-time perception. Engineers must account for how the brain expects visual data to behave in the milliseconds before a sound actually occurs. Let's look at intraoral articulation. The standard engineering assumption has long been that a specific spoken vowel always produces the exact same physical shape of the mouth. Researchers at KTH tested this assumption by compiling the PF-STAR database. They tracked high-fidelity 3D coordinates of facial markers while subjects delivered expressive speech. This chart plots mouth corner displacement. The isolated red cross below is the neutral baseline for a vowel. Surprisingly, the speaker's expressive state drives more variance than the phoneme itself. Under different emotions, the coordinates shift entirely, despite producing the exact same vowel. For developers, static articulatory algorithms are insufficient. The underlying mouth shape equations must be overridden by the agent's emotional state parameters. Emotion operates as a physical modifier of the core articulation engine. It is not an aesthetic layer applied over speech. Shifting focus from the mouth to the upper face, we can investigate how visual cues dictate word prominence, which specific words the listener perceives as heavily stressed. Researchers conducted a perceptual experiment comparing the impact of two subtle visual cues, a 4% eyebrow raise and a slight 3% vertical head nod. In isolated tests, both of these micro-gestures reliably amplified the perceived acoustic prominence of their target words. The critical variable is temporal alignment. If the visual gesture perfectly synchronizes with the stressed vowel, the brain fuses them into strong emphasis. To test this fusion, researchers systematically shifted the visual gesture across the timeline, moving it away from the spoken word. The human brain demonstrates extreme sensitivity to this alignment. A timing error of just 100 milliseconds breaks the intended association between the face and the voice. When that misalignment occurs, the brain executes a fallback mechanism. It forcefully integrates the orphaned visual gesture into the nearest adjacent prominent word instead. Firmly. Timing is absolute. Perfect acoustic emphasis will be completely hijacked by a visual gesture, provided they fall within the exact same 100 millisecond integration window. This introduces a central perceptual tension. How does the brain resolve reality when visual cues and auditory cues explicitly contradict each other? The first conflict experiment pitted physical gestures against each other, a visual head nod on one word, fighting against a visual eyebrow raise on a different word in the exact same sentence. In this scenario, physical saliency determines the winner. The larger mass of the head nod dominates the subtle eyebrow raise, completely stealing the viewer's attention. This visual dominance scales with distance. Moving further from the speaker proves that macro movements are much more reliable signals for word prominence than microexpressions. The second conflict scenario targets syntactic processing. we test the brain's ability to distinguish between an echo question and a declarative statement. The experimental setup intentionally pairs conflicting data, a declarative visual cue, a smile and a short nod, delivered simultaneously with an interrogative acoustic cue, a sharply rising pitch contour. Unlike prominence tracking, syntactic processing heavily favors the acoustic channel. The brain relies on the audio and overrides the conflicting visual input. A rising pitch contour neutralizes any visual head movement attempting to signal a declarative statement. The ear simply overrules the eye. The brain operates on a strict context-dependent hierarchy. Physical saliency dictates which specific word receives prominence, but acoustic pitch governs the overall syntax of the sentence. We can apply this cognitive weighting directly to the engineering of back-channeling, the vital conversational signals an agent uses to confirm that it understands the user's input. This chart visualizes 6 feedback variables, testing parameters from eyebrow frowns to eye closures, isolating the strongest affirmative trigger. The data yields a counterintuitive result. The visual presence of a smile is a stronger affirmative cue than an acoustic pitch contour. We can contrast these dominant cues with the weaker variables at the bottom. Factors like response delay and eye closure show negligible impacts on the user's perception of feedback. To engineer an agreeable, fluent AI, developers have to prioritize visual facial states over acoustic tone. The legacy acoustic-first paradigm simply does not hold up in conversation. Moving from cognitive theory to applied engineering, these exact perceptual data points translate directly into programmatic rules for functional dialogue systems. In the ADAPT system, multimodal cues actively route complex information. The agent uses precise visual signals to manage conversational turn-taking while retrieving dynamic apartment data for the user. The SynFace system applies this strict multimodal parameterization as a real-time speech intelligibility aid for the hearing impaired. Within SynFace, visual turn-taking cues are explicitly engineered into the UI to hide the acoustic latency caused by reconstructing the face image in real time. The visual distraction covers the computational delay. Successful human-computer interaction depends on the precise encoding of multimodal calculus. Our systems must replicate the subconscious temporal hierarchies the human brain uses every day.